Should work. Resume now. Hey everyone, our next speaker is Luka Carroll. He will talk about the presentations for trivial-cokernel partitions and full domain partitions.
Thank you. So good afternoon, everyone. So today I'm going to be talking about some work that I recently completed with James East, Baptiste Fresika, Mengfen Liu, and Aziz Mohammed. In our work, we were looking at certain types of partition algebras, or also known as diagram algebras, namely the trivial co-kernel partitions and the full domain partitions. In particular, we were trying to find presentations for these semigroups. My work on this project was also supported by an MC Summer Research Scholarship and a Western Sydney University undergraduate research scholarship. So before I get to the main results of our work, I'm going to first just briefly go over what a semigroup presentation is and hopefully explain why they're useful. And I'll also introduce the various kinds of partition algebras to help give some sort of context for the objects that we were studying. So in general, the elements of a symmetric group can be fairly sort of complex and messy, but there are also lots of elements that are nice and simple and regular, like this here. We can study these more complex communications like this here by writing them as a combination of these much simpler elements, which we refer to as the generators. The two combinations of generators can produce the same element. So we also need to know, well, what is it that makes these two combinations equal? For this, we use these defining relations. These are a minimal set of rules that should be faithful, they should be true rules, and they should also completely describe what makes two combinations of generators equal. So when we say that Sn has this presentation here, we mean that it's generated by this set here and it's defined by these three relations. So you can see from this result as well that there's been quite a long history in the study of presentations. The reason for that is that they're very useful. In general, when a new semigroup is discovered, one of the first things that you want to do to understand the semigroup is to find presentations. This is because they can reveal some of the underlying structures of the semigroup, but they also reduce the effective size of the semigroup. So, for example, we reduced Sn from this quite large set to this much smaller set of generators, and we've kind of, in a sense, reduced the operation as well from a very large operation to a much smaller operation. This is particularly useful when we want to apply the semigroup in different applications. We want to find representations of the semigroup or use it to define actions. It's much simpler if we can work with these much smaller sets as opposed to these very big ones. There are various ways of generalizing the concept of the symmetric group. So if you think of the symmetric group as bijective mappings from a set to itself, we can generalize that by allowing non-bijective mappings from a set to itself. That gives us the full transformation monoid. We could also generalize it the other way by allowing partial bijections. This gives us the symmetric inverse monoid. If you generalize in both directions, you get the partial transformations. And there's another way of generalizing the symmetric group by allowing, instead of just thinking about mappings between a set and itself, you can think about sort of partial mappings between quotients of the set. This gives us the partition monoid. I'll explain this dotted line in a moment. So the partition monoid is defined as the set of all partitions of the set n union n dash, where n is this set here, and n dash is just a disjoint copy of n. We typically represent these graphically like this, where the connected components of the graph represent the blocks of the partition. Since the partitions are defined by their blocks rather than these edges, we can have different edge sets so long as they give us the same connected components in the graph. The binary operation on Pn is concatenation. You can think of this as a generalization of composition that allows, it handles the more complex connections in the partitions. So here you can see when we concatenate these two diagrams, rather than just focusing on the connections formed between the top and the bottom rows, we also look at all the connections that are formed within the two rows. So the product will be the partition that consists of those connections. The identity element of PM is the same as that in the symmetric group. So the partition monoid is a really rich monoid. It contains lots of interesting sort of substructures, lots of submonoids. Some notable examples include the partial Brouwer and Brouwer monoids. It also contains the dual symmetric inverse monoid. So you can think of the elements of Jn as being bijections or block bijections of a set. And as we saw before, we have these the Tn, In, and Sn are all contained in Pn. The reason for this is that concatenation is equivalent to composition when performed on the elements of Tn, In, and then, of course, Sn. Note, however, that the partial transformations are not a submonoid, even though they are a subset of partitions. They're not a submonoid, as the operation on concatenation is not equivalent to composition on all the elements of PTN. There is kind of an analog of PTN, though, that was recently discovered. This is the trivial-cokernel partition monoid. So this sits in the same sort of place that the partial transformations would. The elements of PNTC are defined as those that have no connections between the vertices in the bottom row of the partition. Another monoid that was discovered recently is the full domain partition monoid. The elements of this monoid are defined as those that have where every vertex in the top row is connected to at least one vertex in the bottom row. There's a nice sort of one thing you notice is that they both intersect in the transformations. The transformations are exactly those elements that have the full domain and trivial cokernel. And you'll also notice there's a nice sort of similarity between the two in that they're both the meat of Tn and some inverse semigroup. So by meat, I mean the smallest monoid that contains the intersection of these two. So this is the meat of these two and the meat of these two. That's the meat of these two. In fact, the PNFD factors into Tn and the idempotence of the dual symmetric inverse monoid, whilst PNTC factors into Tn and the idempotence of the symmetric inverse monoid. Another kind of partition that we'll be considering today are what are called planar partitions. So when we say that a partition is planar, we mean it can be represented without any edge crossings and with all the edges drawn in within the border spanned by the vertices. The set of planar partitions forms a submonoid of Pn, and in fact, for any submonoid of Pn, you'll get a planar version. Some notable examples of these. So a lot of these have been significant objects of interest in their own right. These include the Motzkin monoid, the Templey-Lieb monoid, as well as the order-preserving partial bijections and the order-preserving transformations. So in our work, we were finding that up until recently, there were presentations known for all of these monoids, excluding these four blue ones here. So in our work, we were trying to find presentations for these four new monoids. I won't have time to go over the presentations, all the presentations today. So what we're going to do is going to focus on the presentations for these trivial cokernel partitions. And then at the end, I'll very briefly just give an outline of the generating sets for these two monoids. So for the trivial cokernel partitions, we used existing presentations for these three submonoids. So for the symmetric group, we have the generating set that we saw earlier. The symmetric inverse monoid uses the S generators along with this one E generator. The full transformation monoid uses the S generators and this T generator. And PNTC uses the combination of all of these generators here. So the first main result I want to show today is this presentation for PNTC. So you can see these S defining relations are the same as those for the symmetric group. These T relations in combination with the S relations give us the defining relations for Tn. The defining relations for In come from these S and I relations. And then the last three relations here just describe the interactions between In and Tn. And so altogether, these are the defining relations for PNTC. Here's a few examples of what these relations look like. I won't go through all these, but I'll just point out these first two. They tell us that the T and E generators are in fact idempotents. When we were proving the presentation for the full monoid, as part of the process of proving the presentation for the full monoid, we first found a presentation for the singular part. So in general, since the units in Pn are all in the symmetric group, the singular part of any monoid will be the complement of the symmetric group in that monoid. So for this presentation, we used, rather than using existing presentations for these two sub-semigroups, we were actually able to just use a presentation for the singular part of Tn, as well as one for the idempotence of the symmetric inverse monoid. So the generators for this semigroup look like this, whilst the generators for the singular part of Tn look like this. There's a left and a right-handed version, depending on whether I is less than or greater than j. And so for the full semigroup, we used the union of these two generating sets. So here is our presentation for the singular part of PNTC. Again, we have these relations come from the presentation for this semigroup. These relations come from the presentation for that. And then the last four relations describe the interactions between the two. And so all those together describe the full semigroup. Again, a few more examples. You may notice that these first two relations are in fact special cases of some of the relations, general cases of some of the relations that I showed earlier for the full monoid. This last one though is a little bit more interesting. There isn't an obvious analog of that last relation in the presentation for the full monoid. For the planar part of PNTC, we use presentations for the order-preserving transformations and partial bijections. Although, again, similar to the previous case, we didn't actually need the full presentation for the order-preserving partial bijections. We're instead able to use the idempotence again. So another point worth noting is for any submonoid of Pn, the planar part will be essentially a subset of the singular part. You just ignore the identity. Just the planar part of any monoid is a subset of the singular part. So in this instance, it made no difference because all the elements of this, all the idempotents of In are already planar. But for the order-preserving transformations, we were able to use the planar subset of the generators for the singular transformations. So they just look like this set here, O. And so the set of generators for the planar part of PNTC are these O and E generators. So once again, we've got the last main result that I'm going to show today is this one here for the planar part of PNTC. These O relations come from the order-preserving transformations. These are the E relations that we saw a moment ago for the idempotence of In. And then these last six relations, again, describe the interactions between the two. I won't give an example relations here because it turns out that all of the new relations, these 6 new relations here, they're actually just planar subsets of the relations that we've got for the singular part of PNTC. So that's there are results for PNTC. We also found similar results for the full domain partitions. Just as a reminder, the full domain partitions, they're the ones where every vertex in the top row is connected to something in the bottom row. So there was a lot of nice sort of similarities between there's a lot of nice similarities between these 2 monoids and their presentations. That said, the actual process of proving the results was very different. Despite the similarities, there's still quite a lot that just distinguishes the 2. So I'll just go over the generators that we use for the full domain partitions. Here, instead of using existing presentations for JN, we actually were able to use an existing presentation for a subset of a submonoid of JN. These are the partial block bijections. So, sorry, these are the block bijections. These are the block bijections where each block in the top row is mapped to a block of the same size in the bottom row. And the generators for Fn are just the symmetric group and one box there. And we have our T generator from before for Tn. For the singular part of PNFD, we kind of similar to the previous case, we were able to use the idempotents of Jn. They look like this. So the idempotents of Jn are just the partitions where each block in the top row is mapped to the same block in the bottom row. And so our generators look like this. Finally, for the planar part of PNFD, we just use the planar part of these idempotents, which are essentially the same set, just where none of the blocks are overlapping. And so the generators are the same as here. There's the planar versions for these generators. And I forgot to mention, if you're interested in finding more details about these results, there's a preprint up on the archive. So in terms of future directions, there's a few places we can take the work from here. One of the most important things that will be worth doing is investigating the congruences of these monoids. If you're not familiar with semigroup theory, congruences are a particularly important concept in semigroup theory because they're used to define quotient semigroups and homomorphisms. They play a similar role to normal subgroups from group theory. And the investigation of these congruences can be assisted by systems such as GAP, which will be easy to do now that we have presentations for these monoids. There's also several interesting sub-semigroups of these monoids. So if you take the complement of Tn in both the monoids, you actually get a sub-semigroup. So it'd be interesting to see if we can find presentations for those. And we also came across these interesting, in the course of proving the planar presentations, we came across these interesting monoids that are subsets of PNTC and PNFD. And they have a nice natural unary operation that's connected to them that would be worth investigating. Finally, it would be good to try and find ways to represent other objects using these partitions. Like, we just know how we can embed these monoids in other semigroups, but also how other semigroups can be embedded in these. In particular, it's worth noting that PNFD and its singular part are what are called right restriction semigroups. The planar part of PNFD is a GR rack semigroup, and DN and VN are right and left regular bands, respectively. So there might be some nice ways to represent other right restriction semigroups and left and right regular bands using these. So that's all. Thanks for listening.
Any question for Luka?
What does GRIC stand for? I used to know.
Okay, so I think Generalized right restriction satisfying the ample and congruent conditions. I think it's.
I think it's just ample condition.
Okay, so it says satisfying the ample condition. Yeah. And then the left and right version of this, of course. And there's a dual of P and FT because we were just looking at full domain where everything in the top row is connected to something in the bottom. You can just as easily take the involution and that will give you a GL rack semigroup.
If there's no more question, let's thank Luka once again. Thank you.
Thanks.
It's the end.